Okay, so in the last video, we took a look at non-inertial reference systems and extended that to take a look at the effects of the Earth's rotation. Now, this picture that you see in front of you is, I would like to say, the Foucault pendulum, but there's an asterisk to that I'll get into in a moment. This is located in the Pantheon in Paris, which is actually a desanctified church. So it's a former church, and it's where France has chosen to bury some of its national heroes and scholars. So, for instance, you will find I believe Voltaire there. I know for a fact that you'll find Louis Braille buried there, and other notables. Anyway, Foucault, as we'll see, realized that you could use a pendulum to detect the fact that we were in a non-inertial frame. And he did that by thinking about the precession of a pendulum. Now, in order for this not to turn into a higgledy-piggledy mess, oscillating through a small angle is vital. So, the cable that pendulum bob you see attached there is 67 meters long. And you can see they only pull it out, probably a little less than 2 meters off to one side before they let it go. It's actually also incredibly fussy as to how you let it go. You can't have any sideways motion or it'll all go higgledy-piggledy. So the method that they use, that the curators at the Pantheon use even now, is the same one that Foucault himself devised, which is they pull it back with a string, attach the string to a support, and then burn the knot in the string using a candle. Because no matter how smooth you can release it by hand, it turns out you can't release it smooth enough. So starting a Foucault pendulum is a bit of a pain. Anyway, I did mention that this is a replica of the pendulum. The original pendulum was hung there a couple of times and then was retired to a different museum, and every so often was brought back to the Pantheon for special events. And then it was put back to the other museum, which is a science museum. But it turns out that now it's just the original pendulum bob is kind of a mess because one of the times where it was hanging over at the Pantheon, the cable broke, the bob fell and was dented irreparably, and actually they did a pretty good number on the marble in the floor, and they had to do a lot of reconstruction of the floor to make it all look pretty again. So anyway, that pendulum you see there is an exact replica of the one that Foucault used. And the reason for the choice of the Pantheon was pretty simple. It was 60, he could get a length 67 meters long. It's pretty much that simple. The ring that you see and the little octagon in the middle there, you can see are calibrated. They set it off so that if they let it go at midnight, that's swinging at 0, and they're showing the predicted precession, so you can kind of use this to read the time of day. Okay. So with that, let's go ahead and start analyzing it. So as we suspend our pendulum, pardon me a moment here, there we go. As we suspend our pendulum, keep in mind that this length is very big. It's going to be much bigger than any relevant dimension. In the problem. So there's our pendulum bob there. And if we go straight underneath like so, we're going to set up our coordinate system. Now I'm going to follow your book here and change the direction of the coordinate system from what we just had in the last video. The z-axis is still pointing directly up, and it is directly against the local g vector, the one that takes into account the centripetal force, the centrifugal force. But now the x-axis, we are going to have point to, so the z-axis points up, the x-axis points to the north, and the y-axis points to the west as a result. So we've rotated our coordinate system 90 degrees around the z-axis. Sorry, but I felt it was useful to keep consistent with your text. Okay, so we can go ahead and draw in, I'll draw in our free body diagram. We're going to have the tension pointing along the string, and we're going to have the gravitational field including the centrifugal force, so not mg naught, but mg pointing straight down. Okay, so enough of that for now. Let's go ahead and write the equation of motion for our rotating frame. So we have an external force of T plus our mg from before. So we still have our Coriolis force, 2m omega cross v prime, and we have our centrifugal force, 2m omega cross r prime, which that is approximately 0 because again it's omega squared versus omega, and the omega is due to the Earth's rotation. That'll be equal to our ma prime. So with the choice of coordinate axes that we have, now our omega x prime is equal to minus omega cos lambda. Our omega y prime is 0, and our omega z prime is omega sine lambda as before. All right, now the swing is really small. And you can see the extremes that Foucault went to doing it. In fact, pretty much any Foucault pendulum you build, you really want the pendulum to be a couple, 3 stories long at a minimum. Okay, so with that, we can say that our Vx prime, we'll just say that that's x prime dot. Our Vy prime will be y prime dot. And then we're going to just say that our Vz prime is approximately 0. That will make it a lot easier to analyze. And that's actually fair. I mean, you pull something over a meter or so on a 67-meter long cable, you're not going up by more than a few millimeters, so big hairy deal. All right. While we're at it, we'll also take the components of the tension. The x prime component of the tension is going to be minus t times x prime over L. The y component will be minus t times y prime over L. And then the z prime component is going to be just approximately t, because really we've never deflected that far off. Okay, so now with all of that, we are free to compute our omega cross v prime. So I, j, k minus omega cos lambda 0 omega sine lambda x prime dot y prime dot 0. Okay, so we go ahead and do that. We plow the field, we get 0 this way, and that way we'll get minus omega y dot, so we'll have I prime minus omega y prime dot sine lambda. For the j, this way is non-zero, but that way is 0, so we get plus j prime omega x prime dot sine lambda. And then for the z component, when we plow the field this way, we'll get a minus omega y dot. It's not going to matter anyway. We're going to get a minus omega whoops. Let's try that again. Minus k prime omega y dot prime cosine lambda. Okay, yeah. And then this direction gives us 0. Alright, so now plugging into our Newton's second law and taking components, we will get mx double dot prime equals tx prime plus 2m omega y dot prime sine lambda my double dot be ty prime minus 2m omega x prime dot sine lambda. And then we don't care about it, but I'll just note it parenthetically. Mz double dot will equal tz prime minus mg plus 2m sorry there. Plus we're going to pick up m omega x prime dot sine lambda minus m omega y prime dot cos lambda, but we don't care about this one. All right, so the swing is small, so we can say that the tension is approximately mg, and we already took our components up here. So our system will become, oops, there we go, m x prime double dot is equal to minus mg x prime over L plus 2m omega y prime dot sine lambda, and then minus mg y prime over L minus 2m omega x prime dot sine lambda. All right, small favors, cancel, 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 yeah. All right, now you'll notice here, this is basically already in standard form. Well, except for the stuff sitting over here that we don't like, but let's just roll with that for the moment. So normally we would call g over L omega. So we can, but since we've already got omega taken, we'll let alpha squared equal g over L, or alpha be root g over L. And because this omega sine lambda is going to keep showing up all the time, we'll call that the z. That's the z component of omega, so we'll just call it omega z, just to make it a little easier to write. So with those notation changes, our system becomes x prime double dot plus alpha squared x prime equals 2 omega z y prime, and y prime double dot plus alpha squared y prime equals minus 2 omega z x dot. Well, with primes. All right. Now, that looks pretty hopelessly coupled, but again, when you look at a coupling like this, you should think maybe the method of complex exponentials isn't such a bad way to go. So I just called the x equation A and the y equation B. And so to see if we can't get it into something of a little happier form, we can go ahead and do just that. Let's look at what we get if we add I times B to A. Again, no problem here. We're just keeping the x equation in the real part and the y equation in the imaginary part. And at the end, we can just take the real and imaginary components. All right, so if we do that, we're going to get an x prime double dot plus I y prime double dot plus, we'll group the alpha squared terms, x prime plus I y prime. That will equal, alrighty, we're going to get from that a minus 2I, skipping a couple, well, no, we won't skip the steps, what the heck. So we'll have a 2 omega z in common, then we'll have a y prime dot minus an I x prime dot. Now, I would love this to be an x prime minus an I y prime, and I can do that if I go ahead and multiply here by -1 and there by -1 to flip the order, and then we'll go ahead and pull out an I. So when we do that, we'll get minus 2I omega z x prime dot plus I y prime dot. Yay! So now that I've got this as a second derivative of some nice form, the constant and the first derivative, that allows us to define, say, eta prime. There we go. Let eta prime be x prime plus I y prime. So then we can write our equation of motion as eta prime double dot plus 2I omega z eta prime dot plus alpha squared eta equals 0. Now, when you look at something like this, you should ask yourself, where have I seen this before? So go ahead, ask yourself that. I'll pause, and then we'll get back together on the other end. Okay, I'm hoping that you looked at this and said, geez, this looks like a damped harmonic oscillator, but I'll put damped in quotes. And the reason is that our damping coefficient, that's our gamma there, our damping coefficient is imaginary. So that's a little hanky, but it's okay. The point is, we've solved this before, so we will just go back to when we looked at the damped harmonic oscillator and steal the solution. So you remember when we did that, that was x double dot plus 2 gamma, sorry, that's it. Oh no, I actually even have the 2 gamma there, that's good. So this much right here, the I omega z is my gamma, plus 2 gamma x dot plus omega naught squared x equals 0, we found that the solution was e to the minus gamma t times a times e to the square root gamma squared minus omega naught squared t plus b e to the minus root gamma squared minus omega naught squared t. Cool. So that was our solution. So if we just hold our nose and let gamma be I omega, mathematically we're still all fat and happy. The solution's good in complex space. Just because our gamma is imaginary is not a big deal. So we can recycle it. And when we do, I'll clean it up just a little bit. So our eta prime is e to the minus I omega z t times a e to the square root of minus omega z squared minus alpha squared t plus b e to the minus square root of minus omega z squared minus alpha squared t. All right. So just for a moment, let's just remember what things looked like in an inertial frame. So here omega z would be 0 because the frame is inertial. In that case, our differential equation, so no primes here, would be eta double dot plus alpha squared eta equals 0. And so we would interpret alpha as the oscillation frequency. Just in case we forgot what it was, it's root g over L. And even with a 67-meter long pendulum, and I assure you it takes a while to swing, that's still a lot higher frequency than the rate at which the Earth is rotating. So it's still a lot bigger than omega z. So going back into our normal space, we can look at this and say, okay, these omega z's I can kind of make go away because they're very small compared to the alphas. So I'll get that omega prime is roughly e to the minus I omega zt times a e to the I alpha t plus b e to the minus I alpha t. Yeah, so now we've got a solution that we can use. Now, how the heck do we go about interpreting that? Well, if we go back to the inertial frame case, there the solution would be eta is just a e to the I alpha t plus b e to the minus I alpha t. Okay, so what we get out of that is that what we observe in the rotating frame, eta prime, is what you get in the inertial frame times this e to the minus I omega z t. All right. To interpret this a little further, I think it'll initially be instructive. Eventually you'll look at this and recognize that there's a rotation happening. But I think at least initially it'll be instructive for us to decouple the real and imaginary parts again. So this would be x prime plus well, we don't need the parenthesis there, x prime plus I y prime. This would equal x plus I y times cosine omega z t minus I sine omega z t. That's using the Euler identity. Okay, so let's go ahead and FOIL it out and group out the real and imaginary parts. We're going to get an x cosine omega z t plus y sine omega z t, that's the real part, plus I times, so the imaginary part will be minus x sine omega z t plus y cosine omega z t. All right, so now if we go ahead and equate our real and imaginary parts, we will have x prime equals x cosine omega z, omega z t plus y sine omega z t. And then y prime is minus x sine omega z t plus y cosine omega z t. All right. That should look familiar. That should look like we've done some matrix multiplication. So let's make that thought a little more explicit. We'll express our x and y as a prime as a column vector. So this is what we would get if we multiplied cosine omega z t sine omega z t minus sine omega z t cosine omega z t against our xy. So just as a quick bit of review, how do I interpret this matrix here? Pause it, think about it, I'll get back with you on the other side. Okay, that matrix I did a red underline on, that is a rotation matrix. So this tells me that the angle of rotation for our plane of oscillation, the angle of rotation from whenever we let it go, omega zt, so that angle, I guess we call that, I don't know what we want to call it, I'll just call it angle of rotation there, how's that? That will be equal omega zt, and remembering that omega z was omega sine lambda, that'll be omega t sine lambda, and our angular frequency, omega z, is the rate at which the Earth turns times the sine of your latitude. So let's just say, for some kind of quick comparison's sake here, that you constructed such a Foucault pendulum and located it in Flint, Michigan. That Foucault pendulum might happen to have a surveyed latitude of about 43 degrees 1 minute north. So our omega z would be equal to omega sine lambda. So that would be 2 pi over the period of our Foucault pendulum's precession. This would be equal to 2 pi over the period of the Earth's rotation times the sine of the latitude. Cancel, cancel. All right. So we get that our period of our Foucault pendulum is equal to the period of our Foucault pendulum precession. The time it takes to precess completely, around 360 degrees, is the period of the Earth's rotation over the sine of your latitude. So that would be 24 hours over the sine of 43 degrees 1 minute. That works out to be 35 hours 10.8 minutes. In the northern hemisphere, which is where this one's located, the precession is clockwise. If we're in the southern hemisphere, it would be counterclockwise because the latitude would be negative. Okay, now this is a big deal. This precession only happens because of the centrifugal force that is due to the Earth's rotation. So this is how you finally are able to demonstrate, how you can finally settle the hash experimentally of the question of heliocentrism versus geocentrism, believe it or not. That's why this is such a big deal. There's some intermediate models due to Tycho Brahe and whatnot, but the gist of it is that if we decide to put the Earth at the center of the universe rather than the sun, of course now the correct thing would be to say center. What center? But I digress. If we were to put the Earth at the center of the universe and have the sun orbit around, and the stars orbit around, omega would be 0. So then there would be no centrifugal force, and there would be no precession of the Foucault pendulum. On the other hand, if the Earth is the one doing the rotating rather than the sun, now you predict that there would be a centrifugal force. We can calculate how long it takes the pendulum to precess as a result. And when Foucault set up his pendulum in Paris and computed his period in Paris, the precession period, which is a little different because Paris is a little further to the north of us, so the precession period is a little different. But the precession period matches to the second to what Foucault had predicted. And thus you can finally say that yes, we are on a rotating Earth, and the stars, at least comparatively speaking, are fixed. Okay, the next series of videos we're going to be taking a look at gravitation and central forces in general, and we'll use that as a bit of a case study for how theoretical modeling gets done in the first place.